So, in the previous tutorial, what we saw was that how we can see the single gene analysis using GPA, how we can see the expression distribution of any specific gene in different cancer types, how they are and with what genes they are correlated, and so on and so forth. One thing for this tutorial, what I want to do here is about survival analysis. That, for example, for the same gene, if we want to look for the survival of that gene in multiple cancer types, like we saw it in in um bladder cancer, in lung cancer, liver cancer. And one thing I missed to tell you is that one is GPA, and then there's one another one with as the next version, that is GPA 2. So I would prefer to use the latest version where we have a lot of different more analysis. So what we did in the previous one was that we use FGFR4. So again, I would prefer to use FGFR4 again for this analysis, so that we build up on our analysis, and we can all the viewers can also follow the same suit for other genes as well. So the simply, what is survival analysis? Basically, survival analysis is the analysis or assessment of the gene expression and its association with the survival of the patient. Like whether the so there are different types of survival. Number one is the overall survival, which means that uh, if the patient is the gene expression pattern is has any association with the death or alive of the patient, or like for example there are two options, one is deceased or one is not deceased. So is there any association of the expression of that particular gene with the death, or with with the alive uh, information of that patient? And for that, basically, you can see now these are the options for the analysis. There are two things what we get for the survival. One is the just I told you, like death or alive. The other thing is the survival time, like the follow up time, that how much time the patient was followed in the hospital, and we had the information that whether he or she or is dead or alive. So using the what we do in the survival analysis is that we use the gene expression values, we use the death or alive information, and also the follow-up time information, and combine these three together to do the survival analysis. And the best and the most widely used, or we can say the only used curve or plot, is the Kaplan-Meier's survival plot, and we will see it here. So if you see from here that you don't have to code, you don't have to do anything. You just need to type the gene name here. For instance, like we search FGFR4. We want to see the overall survival. I will explain what is disease-free survival, and we want to classify the gene expression values based on the median. Like the genes which are higher than median will be upregulation, which are lower than median will be downregulation. And then the hazard ratio is actually the it tell that whether the expression has any HR ratio, whether it has an effect on the poor prognosis or good prognosis of the patient, and 95% confidence interval. And yeah, and high expression is for red and low expression is for blue. So median, greater than median would be red, and less than median would be blue. And then these are different cancer type information. For example, I select, as we saw in the previous video, that LIHC liver cancer had a very high expression of FGFR4. So you just have to click it, add it in the data set, and then you just have to click the plot. And when you click the plot, it's taking a bit of time, I don't know why. When you will click it, it will generate a survival plot beneath this whole these options. I think yeah, you can see that it's loading now. It's here, it's almost done. One, two, three, and I was about to say go, but I think it's not going. Let's wait. Yeah, it's taking a bit of time here. So if you so let's wait for it. There's another option that is the disease-free survival. So I'll explain what is disease-free. Difference between the overall and disease-free is that one is the dead or alive. The other one is whether the patient has disease, current disease, or it is disease-free. Like after treatment, the disease is gone, or again it is recurred. So both of these things can be checked by the follow-up of the patient. So yeah, so now the plot is ready. So here you can see that red is for upregulation, that is red. Blue is for downregulation, that is blue here. And what you see here is that on the y-axis is the percent survival. Means that how much percentage of patients are survived with time. And on the x-axis, that's why on x-axis this is follow-up months. Like the information is followed till 120 months. And so we can see that, and blue is for low FGFR expression, red is for high FGFR expression. So we can see that the patients which have a higher expression of FGFR4 had more less percentage of survival, and there are more death events compared to the patients which have low expression of FGFR4. So what it tells is that if the patients have a high expression of FGFR4, there is a more pronounced chance of being dead than alive. And for to statistically validate this information, we go to the p-value. There are different type of uh, probability values, log rank, and there are Barstow and others. Here it has used log rank p-value, which is slightly at a higher scale than 0.05, but it's almost significant. So, but we can say that the patients which have a higher expression has a tendency of less survival compared to the patients which have low expression. And same as if, for instance, if we select the disease free and plot again it will take time as usual. And 95% confidence, you know what is 95% confidence? That this is the highest, the confidence or the probability of have getting the accurate information is 95%, or 5% chance of false positive. And yeah, and you can again you can also see that you can, based on cutoff, like for example I just did for median. Maybe if I do for quartile, I get a better p-value. So quartile is for the highest expression, and the you can do for the lowest expression as well. So here, if you see for disease free, which means that the if the patient has disease or it's disease free, uh, so what we see here is that we have, just like we have the information of dead or alive, here we have information for whether the patient is disease free or whether the patient has a disease. So what? So if there is a disease, then there is an event. Just like if there is a death, there is an event. So here, what we see is that the patients again, which has a higher expression, have more events of having a disease compared to the patients who have low expression. So, and the p-value is now significant, that is less than 0.05. HR is very high. Hazard ratio, if the HR ratio is greater than 1, it means it's a poor prognostic implications of this gene expression. So what we see here with the data is that the the overexpression of FGFR4 has association with poor survival, both poor overall survival, which means either we can say poor overall survival or we can say reduced overall survival, and also we can say that uh, poor disease-free survival or reduced disease-free, uh, reduced chances of being disease-free if the patient has overexpression of FGFR4, right? So in this tutorial, we discussed another interesting feature of GPA, that is to do the overall survival. And yeah, now if again now I have changed the quartile, and you can see that now the p-value is not significant. So you can tweak, and you can change the range. You can also give the custom range. You can do the median, you can do the quartile. So I think that's enough for today, and in the next we will discuss about other features of GPI and other features of cancer genomic analysis. Thank you very much. Have a nice day.